We have reached the last lecture, X28, for the second law of thermodynamics. So, before we begin with the main theme, we summarize what you have studied regarding thermodynamics. We derive the ideal gas equation PV equals NKBT that is valid only if a system is in thermal equilibrium at a temperature T, and only if the system is in equilibrium at temperature T, the pressure and volume of the gas is well defined. If it is not the case, for example, during the time in which a gas is expanding in free space, both the volume and the pressure are not defined, so we cannot make use of this ideal gas equation. So always please remember, we can use this equation only if it is in thermal equilibrium. The next one we studied is the first law of thermodynamics. The first law of thermodynamics is nothing but the conservation of energy. And left-hand side, the dq represents the heat transferred to the system from outside. And PDV is the differential of the work done by the gas against the pressure outside. So even though there is a change in volume, if there is nothing outside, for example, vacuum, in free expansion, there is no work. So this pressure times the volume difference represent the work done by the gas against the pressure from outside. And there is a remnant energy that is being transferred to the heat energy of the gas. So that is a internal kinetic energy. Internal kinetic energy can always expressed in terms of the heat capacity. And there are various heat capacities, but if we do not allow the change in volume, this one vanishes, and all of the heat transfer to the system is by 100% transformed into the internal energy of the system. And if we rescale it in terms of the temperature change, the overall coefficient will be the constant volume heat capacity at a constant volume. And this CV is following the equipartition theorem, number of degrees of freedom of the gas molecule multiplied by the number of molecules and multiplied by 1/2 of Kb, Boltzmann constant. And we have studied the entropy, and the change of the entropy was defined by the heat transfer to the system and divided by the temperature. And according to the first law of thermodynamics, we can rewrite the heat transfer to the system as the work done by the system, and the change in the internal energy. And if we divide this by temperature, we can simplify the expression by making use of the equation for ideal gas. So PV equals NKBT, and P over T equals nkb over v. So we can rewrite this expression in this way. Because among p, v, and t, only two variables are independent, so this expression is very nice to obtain the information of the system, the CV, and number of particles by differentiation. That will be displayed on the next page. And because this is a total differential, and these two variables, temperature and volume of the gas, is independent, so we can integrate both sides to get the information for the entropy. And right hand side, this integral and this integral is a simple integral involving log. And we can replace this CV, that is 1/2 of KB and KB, multiplied by the number of degrees of freedom. So if we substitute the CV with this right-hand side, we obtain the overall factor nkb as an overall factor, and two logs will be combined together in this form. So we have substituted T0 and V0, and correspondingly we can determine the P0 that depends on this equation in such a manner. There's an initial value for the integral. Using this expression, keeping the volume the same, we can find the dependence of temperature from initial temperature to final temperature, keeping the volume the same. In that case, the entropy change is expressed in this way, where the power half of F is multiplied in here. In a similar manner, keeping the temperature the same and only varying only the volume of the system from initial to final, we can find the change in entropy of a gas system. And finally, we have studied the entropy defined in terms of a statistical definition introduced by Boltzmann. And Boltzmann introduced us a very simple way to express the entropy as a product of Kb, that is a scaling factor, the Boltzmann constant, multiplied by the log of multiplicity of the system. And in here, because of this log, the log has been observed already when we derive the entropy definition and entropy formula for by making use of the macroscopic thermodynamic variables. We have a log in here, and log is a very good nature, has a very good nature. We know the log of product can be expressed as the sum of two logs. Because of this, the entropy of a composite system becomes additive. And while this W represents the multiplicity, that is related to the probability of finding a system. And the probability is in usual case, the probabilities of the two systems to be combined together are independent. So independent probability can be computed as a product, PA times PB, something like that. So if we take the log, then this log probability can be added into such a manner. If I multiply the overall factor, scaling factor of Boltzmann constant, then this is related to the multiplicity, WA, WB, but actually the PA is a WA divided by sum of all kinds of multiplicities, microscopic microstates. So in this manner, I can add the entropy of the two systems S cut B is actually the sum of the two entropies. So it becomes a very convenient. So as I already stated, the full expression for the entropy in terms of macroscopic thermodynamic variables, I can take the derivative with respect to log V and log temperature. So I can read off the number of particles multiplied by Boltzmann constant, number of particles multiplied by Boltzmann constant by taking the partial derivative with respect to log V. In a similar manner, the constant temperature, the heat capacity at constant volume can be obtained by, that is this one, nkb multiplied by 1/2, this one, 1/2 number of degrees of freedom. That can be obtained by taking the partial derivative of the entropy with respect to the log of temperature. So we have reached the point to consider the second law of thermodynamics because we have a full understanding of what entropy is. The postulate of entropy is in order that if an irreversible process occurs in a closed system, the entropy of the system always increases. It is impossible for a system to have a transition from a state to another whose entropy decreases. It is always increasing or it is the same. If it is the same, the process is called reversible process because the probability of happening the initial and final state are the same. However, if a process involves the initial states whose entropy is less than that of the final state, the process is called irreversible because the final state has larger probability. So that is called the postulate entropy. And the next one we consider the second law of thermodynamics, that is simply delta S is either greater than 0, that is called irreversible process, or delta S equals 0, that is called reversible process. Okay, this part you can read it through and study by yourself. So as I already stated, entropy is additive. That is a very important point. And the statistical definition by Boltzmann of the entropy is Kb log multiplicity. Suppose that we have a sum of two systems, S1 and S2. They are in thermal equilibrium at temperature T. So we have the system is composed of some the system can acquire some state with the thermodynamic variable, and we may look into the state in a statistical viewpoint to have multiplicities of microstates. For example, we studied when we consider the free expansion of ideal gas from some volume. There are molecules concentrated in some certain volume, and we let this gas expand to wider region. So before it, sorry, before the molecules expand to wider region, then we had we consider this one W1 and W2. Perhaps it is better to write Wi and Wf. Wi, we have the multiplicity of the states and molecules to be placed on the left side only. That is something like that. We can choose only a single beam to let a molecule to be placed. But in the final state, they are distributed over these two equal spaces. Then we have 1 plus 1, the two multiplicities. A single molecule can be placed either on the left side or on the right side. So we have two cases for each molecule, and we have n molecules to be distributed over the whole space. So this multiplicity becomes 2 to the nth power, something like that. These can be treated as multiplicity, and we choose, for example, SI can be computed as KB log this. So this is just 1, so entropy becomes 0. But actually the absolute value of the entropy doesn't mean anything. The only physical meaning comes from the difference between the two states. So in the case of the final state, we have SF is KB log WF. That is KB log 2 to the n. That is NKB log 2. So difference, so delta S is SF subtracted by SI. That is just NKB log 2. Understood? So in that case, if we consider this final state entropy, this is sum of these two components. Okay, what should I do? It should be divided into two pieces. So entropy of the final state is a double of the entropy of the single part. Okay, something like that. So in summary, if a total system consists of the partial systems, in that case, that each system has its own multiplicity. The S2 has a multiplicity W2. Then the net system, the total system, has entropy that depends on W, and that W is the product of two W's, W1 times W2. And the log can be separated in this way. Then we can express the entropy of the total system to be sum of the two systems, sum of the entropies of the two systems. Now we know how to describe the entropy of a composite system. This is sum of two entropies of each system. So why don't we consider a composite system consisting of a very tiny system with a very small energy. And we assume that multiplicity of that state is simply a microstate, is a single state. And we assume that the composite system is closed so that the sum of the two systems, the sum of the energies of the two systems is invariant. So if we vary this tiny energy of the subsystem 1 to be epsilon, then the energy of the other state, S2, is E minus epsilon. And this total energy is kept invariant. It doesn't change at all. And we consider the entropy of the total system. So we focused on the energy shares of S1 and S2. We assume that it is epsilon and sum is fixed, so the energy of the second system is E minus epsilon. Okay? Because the sum is constant, if we take the total differential of the energy, then it is sum of the differentials. Because the sum is fixed to be E, so the energy difference by varying epsilon for the system 1 is d epsilon. And variation of the energy for the second system is this, and this capital E is fixed. Therefore, the dE2 equals the dE that is vanishing subtracted by the epsilon. So we have no change in the total energy of the composite system. As a result, the dE1 and dE2, they are dependent, and we can always express in terms of single linearly independent variation, that is d epsilon. Again, the derivative of E1 with respect to this tiny energy epsilon is 1, and the derivative for the E2 with respect to epsilon is minus 1. At the thermal equilibrium at temperature T, this composite system must have the maximum value of the entropy, according to the second law of thermodynamics. So we are interested in evaluating the change in entropy. This change in entropy must be zero, right? The reversible process. So the entropy change due to the variation of the tiny energy of the subsystem S1 can be evaluated by taking the derivative for the sum, because this entropy of a composite system is a sum of the entropies of the two systems. So if we divide this one into two pieces and we make use of chain rule, so we take the derivative of this entropy with respect to its own energy and multiply the derivative of this energy with respect to the variation of this variable epsilon. The same is true for the second part. And we make use of these formulas. So this identity can be substituted. This is 1 and this is minus 1. So we find that this value must vanish. Why? Because it is in thermal equilibrium, entropy doesn't change at all. It is a reversible process. So because of this, we find that the derivative of entropy with respect to its own energy for the subsystem 1 and subsystem 2 must be the same. But we recall that the entropy change is the heat divided by temperature when it is in thermal equilibrium at temperature T. Because the dQ is the same as the energy transfer, this is dQ is identified to be the E1 for the subpart 1 and E2 for the subpart 2. So this derivative is actually 1 over T, and they are because they are in equilibrium at a temperature T, so it is simply 1 over T, absolute temperature of the two systems in thermal equilibrium. Okay. Now we are ready to find the derived Boltzmann factor that describes the probability of having a microstate for a subsystem that is in thermal equilibrium at temperature T with a heat reservoir. Let us recall the definition, statistical definition of the entropy introduced by Boltzmann. We can rewrite this one S over KB equals log W. So hence W is exponential S over KB. So the multiplicity of the total system is exponential S over KB. The multiplicity of the first subsystem is exponential S1 over KB. And in a similar manner, W2 is expressed in this way. So in order to simplify our analysis, we consider the energy of the state occupied by this first part, is epsilon, and we'd like to vary this energy between, we can compare the probability of the system to the total system to have the energy share to the subsystem 1 to be epsilon alpha and epsilon beta. And so we'd like to compare the probability of the system relatively. So the P alpha is the probability of having the energy epsilon to be epsilon alpha, and probability P beta is for epsilon equals epsilon beta. For simplicity, we assume that there's no additional duplicate microstate, so the microstate is assumed to be a single microstate. If it has additional multiplicity, what we can do is just multiply the multiplicity factor to the whole probability. So in case we have a single microstate for the state alpha and beta, so W1 is 1 for this tiny system for both the case with the energy to be epsilon alpha and epsilon beta. So because W1 is 1, the multiplicity of the whole system is W equals W times 1 times W2, and because this is 1, what we can do is just consider W2 only. And W2 can be expressed in terms of entropies. And this entropy is again expressed in terms of the entropy of the second system. So because this W1 is already computed, it is just 1 for simplicity. So let us find a way to express the entropy of the second system, that is a heat reservoir. We have assumed that the total system is closed. So if one has the energy epsilon, the system 2 has the energy E minus epsilon. And epsilon is assumed to be very small in comparison with the total energy capital E. So we can make an expansion in powers of this small number epsilon. So the Taylor series expansion to the first order, we have this because we have negative sign in front of epsilon. We remember because this system is in thermal equilibrium at temperature T. So this entropy's derivative with respect to its own energy must be 1 over temperature. That's what we have done previously. So we can replace this derivative in terms of 1 over T. So we are all ready. So as a result, just to look at the numerator only first, the P alpha, that is the probability of the whole system in which S1, the W1 is just 1. So this W equals W2, and W2 is expressed in terms of E minus epsilon alpha, and by definition, it is replaced with the exponential, and then we can substitute this expression for the S2 that is expanded in powers of epsilon to order epsilon. So that is to be replaced with this number. Okay, so numerator, denominator, they are identical to each other except that epsilon alpha is replaced with the epsilon beta. So we can combine these two, that is to multiply the negative sign of the power in the denominator. The result is this. So in this expression, we find the leading contribution cancels exactly, and the only contribution, non-trivial contribution, appears in this region, in this term. That gives epsilon alpha with the negative sign, and the contribution coming from the denominator is minus a plus epsilon beta. So we have KB coming from this relation. KB is kept, and the derivative, this derivative has been replaced with the temperature at thermal equilibrium. So as a result, we have arrived at a factor that represents the relative probability of the whole system to have its tiny part S1 to have energy epsilon. That is epsilon alpha and beta. The rate is something like that. That is, it is exponential epsilon alpha over kBt divided by epsilon beta over kBt. So the probability of the system, probability P is proportional to epsilon over kBt. What is the probability? This is the probability of the whole system. S1, system 1 and system 2. And this composite system has a probability when the tiny system has the energy, tiny energy epsilon, and its own microstate, a single microstate. If there is a multiple microstate with the same energy, we can multiply the multiplicity factor in front of this exponential factor. We call this exponential factor to be Boltzmann factor. Now the probability of having the energy E of a single microstate is exponential minus E over kBT. That is called the Boltzmann factor. If there are any other state with the same energy E, then we multiply some number of multiplicity and the Boltzmann factor. So if I want to know the exact normalization for the probability, we had better sum of every microstate, sum of probabilities. So it is just E over kBT, neglecting the over factor for each microstate and sum over all microstates. And divide, we define this one, we denote this one as a partition function. And if we divide the Boltzmann factor by the partition function, that is sum of the Boltzmann factor throughout all possible microstates, then we have a complete normalization for the probability of a single microstate. And actually, this has been used for the Maxwell-Boltzmann distribution for gas molecules in thermal equilibrium at temperature T. And in there, we had the integral over this triple integral for the velocity along the x, y, and z axis, and we had the integrand that is exponential mxi dot squared. I means runs from 1, 2, 3 Cartesian coordinates, and 2 kBt. That's what we obtained previously. This is a product, so it is sum of x1 dot squared plus x2 dot squared plus x3 dot squared, right? So 1/2 mv squared. This is the kinetic energy of a microstate with the x1 dot, x2 dot, and x3 dot. Okay, so summation over every microstate was expressed in terms of the triple integral over the 3 Cartesian components of the velocity. So this is indeed the realization of the Boltzmann factor for the motion of molecules occupying the volume V and with the pressure P in thermal equilibrium at temperature T. So we recall that there is an over factor that is for the integral to be, if we carry out the triple integral, this one should be 1. And if we rewrite this Cartesian integral into the polar coordinate integral, we obtain the Jacobian for radius squared for this three-dimensional integral and the three-dimensional solid angle. Okay. Now we understand the Maxwell-Boltzmann distribution. So next we consider engine. Engine is a cyclical system of consists of the gas, and here we can see the PV diagram of cyclical behavior. The system make a transition from A to B, B to C, C to D, and return to the same position. The engine operates in a cycle in this way, and after a cycle, the entropy G is invariant. What does it mean? Any state P, V, T, and S, every thermodynamic variables return to the same point when it returns to the original position, as long as the system keeps its thermal equilibrium. So the entropy, when it returns to the original point, entropy is invariant, the pressure is invariant, and the volume is also invariant. How does it work? The input energy of an engine is a heat flow from the hot reservoir, and output is the area of this PV curve. During the expansion, this volume increases from A to C. It expands, it does work, and when it returns to the original position, it's a negative work. So the amount of work done by a gas is this area inside the path. So at high temperature, you can draw PV equals N kBT, and P is N kBT over V. At a fixed temperature, this ideal gas equation is of the form. So this is a high temperature and low temperature. And at high temperature, during its expansion, it accepts heat. And when it shrinks to return to the original, the minimum volume, it does work to the outside. No? From the outside, it accepts the work, and it accepts the work, and it gives away heat. So this is the very important point for the engine. The input energy coming from the hot reservoir is not always transformed into the work completely, but there is a remnant. This amount of energy is thrown away. So because this is a positive, though, the lost work is a positive. The lost work is a positive. Minus means it gives away the work. So this amount of work is separated into two pieces: work done by the gas and the lost heat. So the epsilon can never be 100%. So it is impossible to have a perfect engine. Instead, we have indeed an ideal engine that is allowed by physics law. Anyway, because it shows a cyclical behavior, that when it returns to the original point, the starting point, then every thermodynamic variable must be invariant. Hence, the entropy of this whole system is 0. While a perfect engine does not exist, we can consider an ideal engine called the Carnot engine. Carnot engine consists of 4 simple processes. At first, this is the minimum volume. This is volume and pressure. At minimum volume, it keeps the temperature at high temperature. It's an isothermal process, and it expands to volume VB, VA and VB. And this is during this process, temperature is fixed, and because it expands, the system does work. The gas does work. Where does the energy come from? The energy comes from the high temperature heat reservoir. That exact amount of heat is done by the gas, so it does not change. The temperature is kept invariant. And after that, from B to C, it expands further, but there is no heat supply to the system, so it loses its own energy. The work done by the gas is positive during this process, so it is being cooled down to temperature, lower temperature, that is called TL. And after that, there's a maximum expansion until the VC is reached. After that, it keeps the temperature at TL, and TL or T cold, something like that. It shrinks down to the point here, and then again it expands. It shrinks further. During this time, before this adiabatic process, when it is the being cooled down, in here this cooled down to reach C, it keeps the temperature lower temperature. However, the environment does work, so it receives the energy by mechanical energy. However, the temperature is fixed. That means the gas loses its own heat. The amount of work done by the environment to the gas is being transferred. The exact amount of that energy is being transferred to the lower temperature heat reservoir. So there is no change in the internal energy during this time. And then it further shrinks down to have a higher pressure and higher temperature. During the time, there is no adiabatic, there is no heat transfer to and from the environment. So the work done by the gas during this single cycle is the area inside the closed curve. We notice that at high temperature, it accepts heat, and at a fixed temperature in thermal equilibrium, so what's that? The entropy of gas, even though the entropy of the whole system, including the environment, is kept invariant to have the whole reversible process. However, if I isolate the ideal gas from the environment, the gas itself has increased the entropy. And then when it gives away the heat at low temperature, it loses the heat is not supplied but supplied by the gas to the environment. So we have a negative value for the change in that entropy, because we return during this process, adiabatic process, there is no change in entropy, no change in the heat. So the net change of the entropy of the whole cycle should be sum of this. And when it is a zero, it is really cyclical process. So system returns to the same thermodynamic state. That means at any point, P, V, T, and S, all of them are well defined. That means during the whole process, one cycle, the sum of this entropy must vanish. So that is a very strong constraint for the cyclical behavior of an engine. Therefore, we can determine the ratio of the heat transfer from the environment to the system and from the gas to the environment is just a ratio of the temperature. As a result, we can compute the efficiency of Carnot engine. The output is the work and input is the heat coming from the environment at high temperature. We apply the first law of thermodynamics. The work done by the gas must be the difference of the heat transfer from the environment, heat transfer to the environment at low temperature. So we simplify this as this. And then we require that the change of the entropy must be zero under a single cycle. Then the ratio of heat for low and high heat is just the ratio of the temperature of the hot heat reservoir and the cold heat reservoir. In the limit, as the TH hot reservoir temperature goes to infinity, this one vanishes. In that limit, efficiency becomes 100%. However, how can I heat the hot heat reservoir? In total, we need to supply enormous energy to the environment, but effectively it is not actually the 100%. Only in view of the gas itself, it is a 100%, and practically it is impossible to make the hot heat reservoir to have absolute temperature infinity. It is actually inefficient. Okay. So we have seen at high temperature it accepts the heat, so the entropy increases, and during the time when it makes a isothermal shrink, its volume decreases, so it leaves the energy, it gives away the energy to the environment to have its own entropy decrease. And during both of the adiabatic process, there is no change in entropy. A simple engine, in comparison with Carnot engine, that is rather complicated because of the adiabatic process. This is a simple to keeping it at thermal equilibrium. It's all right, but still it is rather complicated because keeping it in a thermal equilibrium, this system should be very slowly interacting. Okay, we cannot change the state abruptly in order to keep the thermal equilibrium. This practical use of a Stirling engine has the structure in this form. Very simple in comparison with this Carnot engine. It consists of two processes. One is what is it? This is a volume. Volume is a fixed volume, and fixed volume. When it has the smallest volume, it accepts the heat. And when it becomes maximum volume, when it requires a maximum volume, it leaves the heat. It gives away the heat. And it does work only for these two processes at higher temperature and lower temperature. Because these two processes are isothermal at higher temperature TH and TL, the calculation of the whole process is quite simple. There is no work during the transition from D to A and B to C, and both of them are isothermal. So it is simple to find the input energy to be like that. So this is the because this is constant volume process in these two processes, we can apply the ideal gas equation and the first law of thermodynamics. And this is the work done by the gas. We know the amount of work is proportional to at fixed temperature amount of work is proportional to the log of a ratio of the volume, and a VA and VAB are fixed. One is log VB over VA. The other, this is negative work, is also proportional to log VB over VA with additional negative sign on it. And we have a proportionality constant for that is temperature, higher temperature subtracted by low temperature. This is the work done by the Stirling engine. It is, they say the Stirling engine is very quiet and it is applied to submarine and further applications. Because I'm not expert, I cannot tell you further, but you can find it further information from, for example, from Wikipedia. So detailed calculation for the Stirling process, including the efficiency, is given explicitly in here. You can follow. And refrigerator is just the reverse the process of the engine. And this is very simple to translate. If you and there is efficiency again appears. Here we write the efficiency of a refrigerator to be K, and in the input is the work. While an engine makes use of heat to transform a part of it into work, the refrigerator makes use of external force, the work, as an input, and output is the heat. Because we want to pull out more heat from the cold place. We want to make something cooler and cooler, right? So input is the work and output is the heat coming from the lower temperature gas. Again, we can apply the first law of thermodynamics, and applying this, and we find the efficiency of a refrigerator, and that corresponds to the Carnot engine. We have the similar formula for the efficiency. All right. Again, cyclical behavior is used, and this, if we keep the whole system to be in thermal equilibrium every time, then the cyclical behavior guarantees that the change of entropy of a single cycle should vanish. So we have this kind of constraint. And similarly to the Carnot engine, we have efficiency formula expressed in terms of temperature. So We are all done with the 28 lectures on the X series of the K-pop guide for general physics. The reason why I do not write K-pop guide 2, but write K-pop guide 4, because I'd like to make physics more familiar to you. Now, people do not want to study physics. It is very difficult, very dirty, and so on. However, I hope you have seen that physics has approached you. Instead, you need to approach physics. So during these 28 lectures, I hope now you can see physics more familiar to familiar rather than the mathematics. For a long time, you have studied mathematics, but you have ignored, and people have ignored, that most of the mathematics class formulas you have encountered came from physics problem. And physics is not that serious as mathematics. It is not confusing. If you feel free to approach physics problem itself, and why don't you make use of mathematics as a tool to understand nature? We are preparing the second series called Y for the second semester, including electromagnetism and relativity, quantum mechanics, and so on. Sure, the electromagnetic wave propagation is another major concern of the Y series. Okay, I hope to see you again in the Y series. I'm preparing for the 2022 version of the Y series. Thank you very much for your listening.